Hello, Mr. Burrell here. We are starting fresh with a new unit. We're talking all about, in this unit, we're going to be talking about exponential and logarithmic equations, specifically how to solve those equations. We just finished in the last unit talking about graphing, a lot about graphing exponential and logarithmic functions, finding inverses of those functions. This unit is all about solving functions that have logarithms or exponential expressions in them. So we're going to start today with solving exponential equations with logs. So before we get there, let me go back here. When you see this number, this symbol right here, what do you think of? Hopefully you think of pi, 3.1415926, etc., etc., etc. Pi is a pretty famous mathematical number. There's a lot of instances in the world where we use pi. It's a pretty cool number. We use it when trying to find the circumference of a circle, or we use it a lot later in trigonometry when we're talking about pi. But there's another really important number in mathematics, and we denote that number with the letter E. E is like 2.71828, etc., etc., etc. It's another really important number. It's another irrational number, just like pi is, a number that is a forever decimal that doesn't repeat and doesn't end. So the number E, otherwise known as Euler's number, because there's this mathematician named Euler that is kind of credited with discovering and coming up with E. This E number is used a lot, among other things, in computing compound interest. So later in this unit, we'll talk about using E in an exponential formula to compute compound interest. There's lots of applications with the letter E in calculus, with the number E in calculus that you'll see in future years. But E is a really, really cool number. Why are we bringing it up right now when we're talking about exponent and log functions? Well, when you see E in an expression, it's just a number. So if you saw something like y equals 2 to the x, or y equals e to the x, that's just an exponential function. This one has a base of 2. This one has a base of 2.718 or whatever, you know. So E is just a number. More specifically, if I had log base E, so like we have log base 2, we've seen log base 10, log base 6, whatever. If I have log base E, mathematicians over time have gotten real lazy, and instead of writing log base E, they instead now write ln. ln is just saying log with a base of a natural number. So this expression, e to the x, is sometimes referred to as like a natural expression. So that's just a way of saying the natural log, or log base E. So just because mathematicians are lazy and they don't want to write that out, you'll often see log of E, log base of E, written as ln. So you'll see that a couple times throughout this unit, so just be aware. By the end of this lesson, I want you to be able to isolate the base and the exponent in an equation, rewrite an exponential equation to a logarithmic equation, which we've already done, and solve exponential equations requiring logarithms. So, in the end of this last unit that we just completed, we talked about changing forms between exponent form and logarithm form. So this might look familiar to you. So for example, with these expressions right here, if I was going to change them to logarithm form, let me move this down for you, this is what it would look like. So 16 equals 2 to the 4 power is the same as saying log base 2 of 16 is equal to 4. Those are interchangeable. Those are the same thing. 7 cubed equals 343 is the same as saying log base of 7 of 343 is equal to 3. Those are the same thing. In an expression like this, before I change forms, I would have to get my exponent expression right here by itself. So I'm going to add 11 on both sides. 9 squared equals 81. And then I can change this into logarithm form. So this would be log base 9 of 81 is equal to 2. Those expressions are the same. So we talked again last unit about changing forms like this. So now that practice, that ability, that tool in our tool belt is going to come in real handy when it comes to solving equations. So now I'm going to give you something like this. I have 11 to the power of n equals 41, and I want you to solve for n. So I don't In this form, it's really difficult to solve for what n is. 11 to the power of what is 41? Well, 11 to the first power is 11. 11 squared is 121. So it's going to be some weird fraction or some weird decimal. How do I know? Well, I'm going to get this n out of the exponent by changing it to a logarithm. So 11 to the n equals 41 is the same as writing log base 11 of 41 is equal to n. Now n is isolated. It's all by itself over here. Well, this right here, log base 11 of 41, we've done that already too. We've talked about changing the base of a logarithm since my calculator only really likes log base 10. So in my calculator, log base 11 is log base 11 of 41 is log of 41 divided by log of 11. And let's do that. Log of 41 divided by log of 11, that ends up being like 1.549. Rounding to 3 decimal places, about 1.549. So we, in our brains, we're thinking, okay, it's probably between 1 and 2, and right there it's about 1.5. 1.549 is how I would solve for n here. So I'm going to follow that same tactic throughout all these problems. So here, first I need to isolate my exponential expression here, so I'm going to subtract 2 on both sides. And get 10 to the n equals 5. Now to get n by itself, I'm going to need to change this to a logarithm. So log base 10 of 5 is equal to n. Well, log base 10 of 5 is like 0.69897-ish, so about 699. That is about what n is. And you can test in your calculator. If you took 10 to the power of 0.6989 blah, 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 plus 2, you indeed get 7. So that's a way to kind of check your work. So as I'm solving expressions like this, we're going to have a variable in the exponent. So the big kicker here, if I'm solving for n in an expression like this, I'm going to need to get that n out of the exponent to get it by itself, and I do that using logarithms. Let's do some other examples like this. So 4n plus 4 equals 102. I'm going to subtract 4 on both sides and get 4 to the n equals 98. Then I'm going to change this to a logarithm. Log base 4 of 98 is equal to n. Well, log base 4 of 98 is really equal to log of 98 divided by log of 4. And log of 98 divided by log of 4, if I type that in my handy-dandy calculator here, I get approximately 3.307. 3.307 is my answer here. That's my n. And again, if I plug that back in for n here, 4 to the power of 3.307 plus 4 will be 102. I'm going to skip this one. You can do this one for practice if you would like. That one's pretty straightforward. Here, now I have a lot going on up in this exponent, but I'm going to follow the same pattern. So I have 3 to the power of r minus 3 equals 88. So my exponential expression right here is already by itself, so I'm going to convert this to a logarithm. Log base 3 of 88 is equal to r minus 3. Well, again, log base 3 of 88, that's just log of 88 divided by log of 3. So let me do that in my calculator. Log of 88 divided by log of 3 is 4.0754. So I just rewrote log base 3 of 88 as 4.0754. That's equal to r minus 3. In these past problems, I would be done. But now I have to add 3 on both sides, because now I have r minus 3. The opposite of subtraction is addition. I add 3 to both sides, and I get r equals 7.0754. So my answer there is 7.0754. And again, if I plug that back in for my r value up here in the exponent, 3 to the power of 7.0754 minus 3 will be 88. Lastly, there's several steps in this problem right here. So I have 2 times 16 to the x minus 1 equals 46. So there's a lot going on. So I'm going to need to get this exponential expression by itself first before I can change it to a logarithm. So I need to get rid of everything else out here. So I have 16 to the x, and then that's being multiplied by 2 if I'm following my order of operations. Then I'm subtracting 1. So I have to undo that in reverse order. So I'm going to add 1 to both sides and get 2 times 16 to the x is equal to 47. Then I have to undo this multiplication with division. So 16 to the x is equal to, what is that, 23.5. Now I have my exponential expression isolated. It's all by itself here. So I'm going to change this to a logarithm. I'm going to use this base over here. So this is log base 16 of 23.5 is equal to x. And how do I type that in my calculator? Log of 23.5 divided by log of 16. And log of 23.5 divided by the log of 16 is 1.139-ish. So that's my x value. X equals 1.139. If you type that in your calculator, 16 to the 1.139 power times by 2, subtracted by 1, will give you 46. So that's what I've got for you. That's what I want you to be able to do. So if I reflect back to my objectives here, I hope you're now able to realize that if you have an exponent that's a variable, you're able to use logarithms to isolate the base and the exponent in an equation. Rewrite an exponential equation as a logarithmic equation, and then solve those equations using what we know about changing the base of logarithms. So that's what I want you to be able to understand. If you need to review back through this video, do some of those examples on your own, feel free to do so. But I hope that was helpful, and I hope that you enjoyed it as much as I did.